Right then, so we are ready to look at ocean circulation now in two chapters. In this chapter, we'll set up the large-scale balances, geostrophy and thermal winds in the ocean, which are quite different than the atmosphere. We will see how. The surface area, mean depth, volume, mean density, and ocean mass are given here. The mean density, you see that it varies by a tiny bit from the density of the fresh water, but this does matter in terms of creating a density driven circulation and in terms of freezing ocean water, producing sea ice, and so on and so forth. Many things are affected by salinity. So the ocean density, it turns out, depends strongly on temperature and salinity, with a little bit of pressure effect as well, even though we have been saying that ocean water is mostly incompressible as opposed to the atmosphere, which is highly compressible. Atmospheric density was highly dependent on pressure and temperature. Ocean is highly dependent on salinity and temperature. The topography of the ocean bottom is choppy compared to land because the deep ocean hardly moves. We will see that, in fact, it moves so slowly that you cannot measure it directly at all. So the erosion is very low, even though water is quite heavy compared to features on land. The ocean topography tends to be choppier, but as we talked before, there are mountains taller than the land mountains within the ocean. And you can see that here in terms of the plate boundaries. This is of course our ring of fire, which has a lot of plate tectonic activities which set off tsunamis and create which set off earthquakes and then tsunamis. So countries like Japan and islands like Hawaii are quite used to tsunamis. There are the mid-ocean ridges and shelf areas of continents where the waters are quite shallow and temperature change can be much more rapid than the deep ocean. So main properties different for the ocean compared to the atmosphere, of course, is that ocean is 1,000 times heavier, heat capacity is 1,000 times higher, but you also see that the ocean has boundaries, except for the Southern Ocean, which is a channel with no boundaries. Okay, so that matters for how much wind energy can go into the ocean. If the winds start to drag the ocean from the east to west by trade winds, then the boundaries at the western end are going to terminate the dragging, because the ocean is not going to go over land, not much anyways. So only 2 to 5% of the wind energy actually gets into the ocean. Okay, there are island effects which create interesting ocean circulation patterns and impacts and biological responses and so on. But having the boundaries produces one of the more interesting features in ocean circulation, the so-called western boundary currents or the western boundary intensification. We have the Kuroshio in the Pacific and the Gulf Stream in the Atlantic, and there is a reversing western boundary current here in the Somali coast region called the Somali Current because of the monsoon circulation changing with the seasons. Albedos for different surfaces. We have talked about how forests, cities, grass, soil, snow, and so on have varying albedos. The main thing about the ocean is that it depends on the angle of incidence of sunlight. So if you are flying in an airplane and sun is on a low angle, then you might get a strong glint from the ocean. But if sun is more overhead and a high angle of incidence, then ocean hardly reflects anything. So ocean can be quite dark depending on at what angle sun's rays are coming in. That matters, of course, for heat uptake by the ocean and energy loss as OLR. Obviously ocean has a huge heat capacity and can produce all kinds of low frequencies because it has all the memories. So if you think about sun being in one hemisphere for 6 months, ocean soaking up the heat, and then going off in the other hemisphere for 6 months, soaking up all the heat, the atmosphere hardly has any memory. Atmosphere's heat capacity is very low, so it keeps no memory from day to day, and which means all the low frequency variability in the climate system have to come from the ocean. So ocean can take up the heat and release the heat on low frequencies at various time scales. The density of water is seawater is heavily dependent on temperature and salts in the ocean. The major constituents are of course the chloride and sodium, which make up most of it, and then they have smaller amount of various other things like sulfate, magnesium, calcium, potassium, bicarbonate, etc. Nonetheless, the seawater that we kept saying is almost incompressible does have a compressibility effect because the ocean on average is 3.7 kilometers deep, and the pressure, because of the heavy water, increases by 1 atmosphere as you go from the surface every 10 meters. So as you go deeper and deeper into the ocean, water does have compressibility effects, and we will see that can mostly be taken in as the pressure dependence of the thermal expansion coefficient of water. So water is highly sensitive to temperature changes, which matters for sea level rise and so on, for example, but also for feeding the atmosphere, evaporation and energy into the atmosphere. Remember the deep convection we kept talking about in warm latitudes? All that is fueled by water that's mostly coming from the oceans, right? So there is infinite supply of water vapor from the ocean that's going to drive our weather and climate, and hence the northward transport of energy that we talked about a lot. So those are the basic properties that we recap for this first podcast, and slowly move into our large-scale balances with a ocean characteristic to them.